Hello, let's talk a little bit about fluid statics, and then we'll get into fluid dynamics a little bit later on. Physics 2 is basically divided into two parts. The first part, we are building up to the world of thermodynamics. The second part, we are dealing with electricity and magnetism. So here in the first part of Physics 2, we're going to start with fluids. Fluids broken into two categories: fluid statics, that's when fluids are just staying still, and then fluid dynamics, and that's fluids in motion. And all of that, both of those things will be relevant to thermodynamics and heat engines and making us able to harness the power of heat transfer in order to do interesting things. So right now, we just need to understand fluids a little bit. So first of all, we have density. This shouldn't be a new concept to you if you've had any, probably biology, chemistry, geology, somewhere in there you've heard something about density. It's going to be mass divided by volume. So it's the amount of mass that a object has divided by the volume that it takes up. Now, in your other scientific pursuits, you may well be used to doing things in grams per milliliter or grams per cubic centimeter. But as you've probably figured out by now, physics is a little bit obnoxious. So we do our mass in kilograms, which is different from everybody else, and we do our length in meters. Therefore, if we do length in meters, we do area in meters squared, and we do volume in meters cubed. What that means on a practical level is that everything you thought you knew is now different. So if you look down the list here to water, water has a density of 1,000, so 1 times 10 to the third, 1,000 kilograms per cubic meter. So if you're converting grams per cubic centimeter to kilograms per cubic meter, what you would do is there's 1,000 grams in 1 kilogram, and there's 100 cubed centimeters cubed in a meter cubed. So you're going to wind up multiplying by 1,000,000 and dividing by 1,000, and then you get your answer as 1,000 kilograms per cubic meter. Other materials have different densities. So we have aluminum, brass, lead. Different things have different densities. So there you go, solids, liquids, and gases. Good time to mention that when we're talking about fluids, fluids aren't solids, but fluids are liquids and gases. Liquids or gases cover the category of fluids. So you've probably figured out the trick of physics and physics equations by now. If density is mass over volume, and that symbol for density is rho, not the little p thing, but you can call it the little p thing if you want to, rho equals m over v, then there's three different questions I can ask you, right? So I can ask you, hey, what's the density of this thing if it has a mass of 5 kilograms and a volume of 1 cubic meter? And then you would say, oh, the density is 5 kilograms divided by 1 cubic meter. That's 5 kilograms per cubic meter. I could also ask you, what is the mass of this thing if it has a density of whatever and a volume of whatever? Then the other question I could ask is, what is the volume of this object if it has a density of whatever and a mass of whatever? There's three different questions I can ask. I'd have to give you the other two unknowns, but you would be able to solve any of those. So this first example is the body of a man whose weight is 690 newtons contains about 5.2 times 10 to the negative third cubic meters of blood. That sounds like maybe not so much blood, but remember that's in cubic meters. Cubic meter is huge. It's a huge amount of volume. So find the blood's weight and express it as a percentage of body weight. So the mass of the blood is going to be mass equals volume times density. So the density, you aren't expected to memorize the density of everything. I will give you a table like this on a quiz or exam, but you'll look and you'll say, oh hey, there's the density of whole blood at 37 degrees body temperature, 1060 kilograms per cubic meter. So 5.2 times 10 to the negative third meters cubed times 1060 kilograms per cubic meter gives us a mass of the blood of 5.5 kilograms. Remember, weight equals mass times the acceleration due to gravity. So 5.5 kilograms times 9.8 meters per second squared gives us the weight of the blood is 54 newtons. And then if we just want to get cute and figure out what the percentage of the body mass that is, we can do 54 divided by 690 newtons times 100 and get it 7.8% of the total body weight is the blood in a typical person. All right, extending our discussion of fluid statics and different things that happen with fluids, different things that we might measure, one of the things that we'll be interested in is pressure. Pressure equals force over area. So in physics land, we do force in newtons. You're probably used to that. Area in meters squared. And we're going to call 1 Newton per meter squared a Pascal. So that'll be our unit for pressure. If you're paying attention, playing along at home, you'll notice that our units in physics are different from what you're maybe used to from chemistry or biology or something else. So sorry, but that's, so pascals is our unit of pressure. So we have this swimmer. Suppose the person's not dead, she's just floating. Sorry that it's creepy. Suppose the pressure acting on the back of a swimmer's hand, why are we looking at her hand in particular? I don't know, is 1.2 times 10 to the 5th pascals. The surface area on the back of the hand is 8.4 times 10 to the negative third meters squared. Determine the magnitude of the force that acts on it. Discuss the direction of the force. So again, we have an equation with 3 components, pressure, force, and area, and given 2 of these components, we can solve for the third. So again, if we're given force and area, we can figure out pressure. If we're given area and pressure, we can figure out force. If we're given pressure and force, we could figure out area. One of those 3 things will come to us. So in this case, determine the magnitude of the force. Gee, I want to find force. I have pressure, I have area. I can figure out the force. So rearranging the equation, solving for force. Force equals pressure times area, and I get a force of 1,000 newtons. Now, here's a case where we're going to talk about the direction of the force. Since the water pushes perpendicularly against the back of the hand, the force is directed downward in the drawing. So we'll talk about this some more. In water, pressure is felt everywhere from all sides of an object that's submerged in water. That's our example of water. In air, here we are sitting in a pool full of air. Air pressure is pushing on us from all sides. So in this case, I guess we're looking at the back of her hand. the water that's on top of her hand, and indeed the atmospheric pressure on top of the water on top of her hand, is all pushing down from the top to the bottom. It's also pushing up from the bottom to the top. Remember, net force equals mass times acceleration. So if her hand is not accelerating, then the net force has to be zero. So all the forces acting on it have to cancel out. And I think that's what they're trying to show with her hips there, is that there's forces pushing from either side on her and they cancel out. All right, I mentioned atmospheric pressure because there is atmospheric pressure. We can think about it as the weight of the column of air sitting on top of our heads. There's air that extends up through our Earth's atmosphere. It gets thinner and thinner till it basically goes away, and then you're in the vacuum of space. But if you were able to kind of measure the weight of that column of air, it's considerable. There's a lot of air sitting on our heads. Our bodies are adjusted for that. We have internal pressure in our cells, and external pressure is required. And if you go deep sea, if you go diving in the sea deep down, then you'll have to get acclimated to higher and higher pressure, because water is even more dense, more massive than the air that's sitting on top of us, so that can be a serious increase in pressure. And if you go to a low pressure environment, that can be bad for you. We're adapted for a pretty narrow range of pressures. So this is a classic experiment where you just pump air out of a can, and then what's happening is you're not crushing the can by squeezing the air out of it. The atmospheric pressure is crushing the can by way of the force, the net force, the internal pressure versus the external pressure. If the internal pressure is lower, then we'll have a case where it's going to be crushed. All right, pressure and depth in a static fluid. This is a big concept, and I want to save it for a fresh video, so we'll take a little break right now.